Welcome. Today we're going to talk about integrated rate laws for second order reactions. For the hypothetical reaction A going to products, just like we've been doing for zero order and for first order reactions, we can write a rate expression where the rate is equal to the change in the concentration of A divided by time, and that's a negative because it's a reactant, and so the change in concentration would be negative. We want a positive value for our rate. We can also write a rate law where the rate is equal to K, that rate constant, times the concentration of A squared. So once we have those two expressions in hand, we can set them equal to one another and then do some math. So let's set these equal to one another. And then using calculus to solve for this relationship, we find the following relationship. We find that 1 over the concentration of A at time t is equal to KT plus 1 over the initial concentration of A. And if we look at this expression, we see that we can envision it as a straight line, as a y equals mx plus b equation, where 1 over the concentration of A at times t is our y, mx is k times t, so our slope is the rate constant, and then our time is going to be on our x-axis, and the y-intercept is 1 over the initial concentration. With this in mind, if we were to graph this data, finding that the plot of 1 over the concentration of A with respect to time is a straight line, that is going to give us evidence that we have a second order reaction. And just like we did before, once we know that we have a second order equation, we can solve a variety of problems using this rate equation. So let's take a look at two problems that we can solve using this integrated rate equation. So in the first problem, we have two iodine atoms reacting to form diatomic iodine. Second order reaction, our rate constant is 7.0 times 10 to the 9th liter per mole second. And we're told that the initial concentration of iodine is 0.086 molar. We want to know the concentration after 2 minutes. So we have our integrated rate equation off to the right. What we simply need to do is plug our values in. So we want to know the concentration of iodine at time t, so at 2 minutes. We know that the rate constant is 7.0 times 10 to the 9th liter per mole second. Our time needs to be in seconds because the rate constant has units of per second. So 2 minutes is 120 seconds. And then to that, we're going to add 1 over the initial concentration, so 1 over 0.086. At this time, all you need to do is multiply and solve for the concentration of the iodine, recognizing that that concentration of the iodine is in the denominator. So once you plug the numbers in on the right-hand side of the equation, that gives you the inverse of the iodine. So you can take the inverse of that value to find the concentration of iodine, which in this case is 1.2 times 10 to the negative 12th molar. Similarly, we can use the integrated rate law to calculate the time needed for the concentration to change by a certain amount. So on this second one, down here, we know that my final concentration is going to be 0.30 molar. We know that we have the same rate constant because it's the same reaction. So I've got 7.0 times 10 to the 9th liters per mole seconds at this temperature. I'm trying to solve for the amount of time it takes to go from from 0.6 to 0.3 molar. And then I'll do 1 over my initial concentration, 0.60 molar. So here again, it's just a matter of doing the math. And so when you solve this particular problem, you're going to end up with a time that is 2.4 times 10 to the negative 10th seconds. So it's very fast. And I want to point out at this time that this is formally a half-life, but we're not going to talk about a nifty half-life equation. Remember, a half-life is how long it takes for your concentration to decrease to half of what it was. We're not going to talk about a nifty half-life equation for zero and second order reactions because they do depend upon the initial concentration, and so they're not as useful.